All right, well, hey, welcome to day 2 here of Modern Physics, Physics 208. Plan today is to kind of pick up where we left off, talking about light and some of the properties of light. We'll hit things like why rainbows form. Today, we'll talk about how polarization occurs. Polarized sunglasses help cut reflection down. And we'll even start talking about images that we see from reflections, like how mirrors work and why we see what we see. So that's what we're going to be doing today. Before I do that, though, any questions about what we talked about last time? Any questions on the homework or anything you'd like to talk about? So, Victor, your question there, how does reflection work if we think of it as a wave? Okay, so if you think of it as a wave, it basically follows what's called Huygens principle. Huygens principle says that when you have a wave, any kind of wave, so it could be light, sound, physical, like wave on the ocean, that every point on that wave front acts as a point, kind of like a drop in water, and you start getting rings that come out. And so what will happen with reflection is basically when those wavefronts reach, actually, you know what, let me do this. I just realized that my little tablet thing's not plugged in. I'm gonna plug in my tablet so I can draw a picture here for you guys instead of moving up to the whiteboard just yet. Sorry about the earthquakes there. Okay, let me share a whiteboard. All right, so this is kind of the idea of Huygens principle. So let's say we've got a wave front, okay? So this line, think of this as the crest of the wave, the high point. And let's say that it's going this way, right? So what's gonna happen, of course, is that crest is gonna move, and it's gonna move, and we'll get a series of crests. The valleys, the low points in the wave are in between, right? But there's our wave that's coming. So Huygens principle, the idea is that any one point on this wavefront is going to act like a point source for a wave. So it's going to create little semicircular things that radiate from that point. But the same thing's going to happen with all the points. So let's say we got one down here, and it's going to do the same thing. Right, and then I'll put one more on here for good measure. So let's say we're down here. So it's going to radiate out waves and so on. And so if all of the points do that and form these little wavelets that are coming out, what's going to end up happening is you're going to get all kinds of arcs from all of them. And the next thing you know, it forms a wavefront. Right. So that's what Huygens principle is all about, is that those wavefronts, when you hit the or at any one point, they're radiating out like ripples on a pond. Okay, so let's think about reflection then. So we got this thing coming in, we've got a wave coming in, and let's go with the surface. It's like, let's say this is the surface that it hits. So when we are looking at this as rays, so first of all, we had our orthogonal, and as a ray coming in, like let's say, oops, that's our ray. So here's our angle of incidence. And we knew that it was going to bounce off at the same angle, right? So that's how we thought about it as rays. Now, if we think of it as wave fronts, kind of like over here, those wave fronts are perpendicular to the ray, right? So what's going to happen when it gets in here? Think about the edge that first hits. So we'll just go at this point right here. Now, when it reflects off, at that moment, it's going to act like a point source, just like over here. And so it's going to make the little semicircular things popping out, right? Well, in a little bit of time, then we're going to run into the same thing happening here, right? So you start getting this one and so on. And notice what happens is that, how many did I have? 1, 2, 3, 1, 2, 3. I think that's probably that point right there. If I connect the dots there, we have this one, and I'm going to have that one. So there's my new wavefront. And I'm going to get them that are parallel to that. And you can see how those are perpendicular to this piece right here. So in terms of why the angle ends up being the same is actually the geometry of those circles. If you look at the circles and you look at where they're intersecting as, assuming that those circles are increasing size at a constant rate, because the speed is the same, right? The speed shouldn't, the speed of the wave is the same because we haven't changed media. So since it's moving at a constant speed and you look at the geometry of it, it turns out that those wave fronts are going to be reflected with that same symmetry. Anyway, so did I interpret your question correctly? And then B, did I explain it well enough? Yeah, that's better. Okay, cool. Yeah, it is kind of interesting that we can basically choose how we want to look at these things. Do we want to look at them as waves? Do we want to look at them as rays? And it turns out it doesn't matter. It's equivalent. But it's just because of the geometry, and it really is because of Huygens principle, because you're dealing with circles, and the rays are radial lines of the circles. And hopefully you remember that pretty much all you need to define a circle is a radius and a point. Well, the point is any old point on that wavefront, and then your radius is being determined by the radial lines, the rays. And so, and they're always, radial lines are always tangent to the curve itself, right? Like you think about a circle, and you're coming out on a radial line that's always perpendicular to the circle itself. And so that's why we get the wave fronts are always perpendicular to the rays. And I don't know if you remember, but like when we dealt with planes, and we wanted to talk about like the direction of the plane, we could always just look at the direction of, we looked at the direction of the normal vector and then went, okay, well, the plane then is perpendicular to it. And so it changes in the vector were enough to make changes in the plane. It's exactly the same deal with rays and wavefronts. So if there's a change in a ray direction, you're going to get a corresponding change in the wavefront directions because of the fact that they are perpendicular to each other. So it's really geometry that lets us do that, and the fact that Huygens principle holds that the waves are basically created by a bunch of little circles with circular wave. Anyway, but good question. I like that one.
I missed the question. What was the question?
Victor was asking about how the reflection property works if you think of it as a wave.
Okay.
Instead of as as the ray, because like when we talked about it, it was all about the ray and the angle of the ray coming in, which is more of the particle idea of light. And so yeah, the question was, what about the wave interpretation? Does that
Got it.
All right, other questions? None yet? All right, well, then I guess I haven't, I'm either explaining things really well or I haven't gotten anything crazy enough for you yet. So let's see if we can do that today. All right, so I want to talk about rainbows. I want to talk about rainbows, how they're formed, why we see them, and what's going on. Right, so you guys all know rainbows. You've seen them. You've probably been awed by them at some point. You may even been taught at one point in time that if you go find the end of it, you go find the treasure with the leprechauns or whatever, right? But the question really should be, why are we seeing that? Why are we seeing these bright colors in the sky in the form of circular arcs? Right? So luckily, just like everything else, well, maybe not everything, but just like most things, we can actually explain it and see what's going on. So let me hop up to the whiteboard and we'll start talking about this thing called dispersion. So I'll be right back. All right, so rainbows are due to a fact, or due to something that we call dispersion. All right, now dispersion, if you think about the word, if we talk about something dispersing, right? When like the police come up to a crowd, please disperse, right? When we talk about things getting dispersed or dispersing, they're getting spread out, right? They're getting sent away, they're getting separated out, things like that. And so that's what dispersion is when we talk about light. This is the fact that the different wavelengths of light get separated. So hopefully you know a little bit about the electromagnetic spectrum, like you guys learned last quarter in E&M. But the light that we see, visible light, is made up of all kinds of different wavelengths. And it's also made up of all kinds of different colors, right? Like when you see a color, what you're seeing is the light that's either reflecting off of it or being transmitted from it of that specific wavelength. I'm just curious if you guys remember anything about them. Do you know what the wavelengths are for visible light, like roughly how big they are?
Bigger than a microwave, I guess.
Okay, yep, they're definitely bigger than a microwave.
They're a little bit lower than ultraviolet.
Okay, so so we've got like ultraviolet is just on one side and just on the other side is infrared. It turns out the wavelengths are all a little bit bigger than ultraviolet. The frequencies are smaller, but the wavelengths are a little bit bigger. Anybody know a number for them at all? And remember, no is a perfectly fine answer. Okay, so Ralph just said 4 times 10 to the 7th to 7 times 10 to the 7th. And I'm guessing you're going to say that those are in meters, right? So the wavelengths for visible light are in nanometers. That's what we tend to see them as, right? And so let me just put this up here. So visible light, it ranges from reds down to the purples or the violet, right? And then we get all the other colors along the way, right? You probably learned somewhere a little mnemonic device or something for the color order, but it pretty much goes red, then oranges, then yellows, greens, and then blues and violets, right? So that's the general order here. And for reds, these are all, well, kind of on the edge of visible light is going to be 650 nanometers. And nano, that's 10 to the minus 9, right? So you could think of this as 650 times 10 to the minus 9, or 6.5 times 10 to the minus 7. So Ralph, you were on the right track. You just gave me some positive exponents instead of negative exponents, which kind of matters, but you were definitely close there. All right, so it's on the order of 650. Now, different people can see different things. Like some people can see up to like 700 and all that, but it's around 650. And then the violet, those are down around 400 nanometers. So again, that'd be 400 times 10 to the minus 9, or 4 times 10 to the minus 7. So those are the wavelengths that we actually see. And so like when sunlight comes to you, or if you see something reflecting off light, right, it's a combination of all of them. All of those wavelengths are all in there forming the white light. Okay, but what happens with dispersion is the wavelengths, the different wavelengths start getting split apart. And you can see this pretty easily, like with a prism or something like that. Hold on one second here, guys. My phone evidently came out because all of a sudden it said running out of power. All right. Anyway, so you can see this pretty easily with like a prism, and I'm sure that Kathy will have you do this in lab at some point, where you'll play around with dispersion. And so you can actually see the colors split. Isaac Newton was the first one to really see this and play with it. But he realized that this light that we see that we don't think has color is made up of all these different colors. All right, so the question is, why is dispersion happening, right? So like if I were to draw here a prism, okay, so we're just like looking down on this, and we were to shine some light into it. So we'll just have, I'm trying to decide what color I want. We'll go sort of teal. All right, so here's light that's coming in. Now, what we know about this light that's coming in is that it is going to refract. It is going to bend as we're going from one medium to another. So let's say we're going from air into glass. All right, so if we were to put in our perpendicular here, if we're going from air into glass, we're going into a bigger N, which means we need a smaller angle. So that means that it's going to bend towards the perpendicular. So it's going to do that, right? And then it hits the other side. Same thing's going to happen. As it passes through, it's going to bend again. But this time, since we're going from bigger N to smaller N, we're going to get a bigger angle. So that means it's going to bend further away from the perpendicular. But we would see that happen. Right? So that would be the path of the ray. But what we actually see when we look at this, if we were to look at different colors, so we'll start with red. Let's say that this is the path of the red. Okay, so light comes in and the red follows this path. What we're going to see is that the purple follows a different path. And then we're going to see everything else, all the other colors between red and violet, do something similar. All right, so there's going to be a blue line, blue light that kind of comes in here. There's going to be the green light that bends at a different rate. And then there's going to be the orange and the yellow and so on. All right, so by the time we're done with this, what we're seeing is that this light has spread out. Instead of it all following the same path, right? It didn't just follow that teal path. It actually split into a bunch of different colors. And that's dispersion. All right, that's the different wavelengths of light get separated. All right, so why? Why does it do that? What do you guys think? I mean, I guess we could be lazy and we could just say magic, God, insert favorite non-describable thing. But what's going on physically?
They're entering at different velocities.
Okay, so maybe we've got different velocities. In terms of entering, they're not entering at different velocities. The light is all coming in at exactly the same speed.
Exiting.
Okay, but there's definitely something, their velocities are changing, right? Because that's what causes the bend anyway, right? When we're talking about refraction, what determines your refraction is the speed that you're moving in that medium, right? We use the index of refraction, the n. And so that's actually exactly it, Jesus, is that it turns out that different wavelengths travel at different speeds, believe it or not. They travel at slightly different speeds in a medium, so that n values depend on the wavelength. And that's kind of trippy. And it was, I mean, it's kind of surprising. I know Newton was really surprised when he saw this. But the reason that this is happening is that the n depends upon lambda. Lambda is the wavelength. So it turns out, like, you know, when I talked about how water has an n of 1.333,
That's not true for all wavelengths. There is some variation. It's not huge variation, right? It's not like, red is going to be 1.333 and purple is going to be 2, right? It's not huge variation, but it might be, okay, red is 1.333 and orange is 1.335. And we might make our way to purple being 1.4 or something, right? But it's enough that it can lead to spread and noticeable spread when it's long enough distance. All right, so that's how we start getting this split of the different wavelengths, and really the reason that you don't always see it is because the geometry isn't enough to exaggerate it. Prisms work really well at this because of the tight angle between entrance and exit. Okay, so that's why we don't always see it. But you see it a lot more than you probably realize. Have you ever noticed it happen like in glass? I'm just curious, like on a sunny day as the sun's hitting your window pane, have you ever noticed it kind of splits a little bit into colors?
Yeah, I've seen that.
Or like Victor said, bubbles or oils.
Okay, so we see it a lot with bubbles and oils. That's actually a completely different thing. We'll talk about that too, like why we see the swirls of colors on bubbles. But even just like through regular old glass, you'll sometimes get this dispersion just because the angles are just right. And you have enough, I was going to say time, but it's more enough distance for the split effect to be noticed. Okay, so this is dispersion. The n varies with wavelength. And so because of that, the angles of refraction are going to vary, which means they're going to follow slightly different paths and they're going to split up. All right, now that's not enough to explain a rainbow, but it's the start, right? We got to have this dispersion happening. Let's see, how can a laser have color? We'll talk about lasers later. But lasers have color because all of the light that's being created by the laser has the same wavelength. So like if you've got a red laser, all of that light that's being created by that laser is the same frequency, the same wavelength. And so it's red. And then you get different colors of lasers by having different materials. We'll talk at length about that in at least a month. It's going to be a while till we get there. But it all has to deal with energy loss, basically. When you lose energy, one of the things that is produced is light. I mean, that's why the sun works, right? It's creating energy that's then getting sent out, as light. And so lasers are designed so that you get very specific wavelengths, but we'll get to that. We'll get to that later. All right, so dispersion happens. Now, it turns out that if you think about it, it kind of makes sense that the n value should depend on the wavelength. Because remember, n is a ratio of the speed compared to the speed out in a vacuum. And different wavelengths are going to interact differently with materials, right? Smaller wavelengths are going to be less affected, or it's the other way around. Bigger wavelengths are going to be less affected by small things getting in the way, right? And so it makes sense that actually the purples get slowed down more than the reds. If you just think of it from the molecules of the material are getting in the way. All right, well, anyway, so we get dispersion. So now why do we see rainbows? Well, rainbows are kind of cool because it's a combination of all three of these things that we've talked about: reflection, refraction, and dispersion. All right, so here's the deal with rainbows. So let's take a water droplet. Right, so there's a water droplet that's in the air. Okay. Now, light's going to enter it. And if we'll just follow like one ray again, like if the light weren't to split apart, this is what it would do, right? It's going to come in. All right, so let's kind of follow it along. So we're going to have our perpendicular to it. Does this, so it's going to bend. And it's going to bend closer to the normal. So it's going to come in and do that. All right, now when it hits the other side, some of the light is going to pass through. But some of it's also going to reflect. So if that's our normal, then we're going to get a reflection that does this. Now, when the light hits this part, same thing's going to happen. Some of it's going to get reflected and some's going to pass through. Let's look at the part that passes through. So, and we're going to go further away. So it's going to be like that. So light that enters a water droplet, some of that light is going to come back. It's retro-reflected, but not all of it, right? And this is the other kind of crazy thing, that once you have materials that light can pass through, you get all kinds of rays going on. Like there is going to be the one that then comes through here and just continues going. There's also going to be one here that reflects. There was also a reflection here. Right? This ray, when it hits this side of the water, well, there's going to be the part that reflects. There's also going to be the part that passes through. And so one ray of light all of a sudden becomes many. Right? And the same thing here, like this piece, some of that comes out. There's also some that reflects, and just like going and going and going. But each time some of the energy, the initial energy, gets lost or separated. So each one of these things gets dimmer as they go. The intensity drops out. But there's a lot of this going on. I'm really only concerned with the blue piece, because that's the part that's going to give us our ring. All right, so let me erase all these other guys, because we don't actually need them, and they're just going to kind of muddle everything up. All right, so that's what would happen with just good old light, one beam. This is what happened. And in fact, if it were monochromatic, meaning all the same wavelength, like from a laser, we would see exactly this. It wouldn't split because it's all the same wavelength. Right, so like if your incoming beam of light only has one wavelength, it cannot disperse. All right, but sunlight that's coming in like this is not just one wavelength, and so it does disperse. All right, so let's just kind of see what happens when this goes on. So I'm going to draw a red line and I'm going to draw a purple line as the two ends of the visible light spectrum. we'll have all the other colors in there as well, but I don't want to get it too muddied up here. All right, so this is going to split into two, or into all the different colors. And what we're going to see is that the red and the purple are going to split in this way. So if we've got a red, let's say, that comes here, the purple is going to bend a little bit further away and do something like that. Right, same kind of picture that we saw over here, where the red and the purple will split this way. Okay, now those are each going to reflect. There's that purple, and then the red, its reflection is like that. So they end up crossing each other, where the purple is now on top, the red is on the bottom. But again, that's just from the symmetry of the reflection. Okay, and then again, those are, when they come out, they're going to get bent. And so this purple is going to bend a little bit more. And the red is also going to bend a little bit more. But that's what happens with the dispersion as it reflects. So the only thing that really happened with that reflection is it inverted it. So the purple is now on top instead of the red being on top. And then the second pass through here, the second time that we actually have refraction, made it so that they spread out a little bit more. All right, so all the other colors are in there as well, right? And they're going to follow similar paths, but you're going to see, for example, there's going to be an orange that's coming here. There's going to be a green. This, there's going to be a blue, and so on. All right. So now remember, what we see is the rays that are coming back to us, to our eye. So we're actually going to see this rainbow if our eye is over here. Okay. So here's the setup, and this is why we see rainbows. Now, I don't know if you've ever noticed this, but anytime you've ever seen a rainbow, where's the sun been relative to you and the rainbow? Can you picture that?
The last time I think I saw a rainbow, the sun was behind me, relatively.
Okay. Well, that's good, because it has to be that way, right? I mean, look at how this is drawn. We're seeing those lights come back to us. So these are all the rain droplets over here that form the rainbow. That light had to come from the same direction as us, which means the sun is actually behind us. So the only time you'll ever see a rainbow is if the rain, water droplet, whatever in the sky is on the other side of you than the sun. So if you ever see a picture that has the sun and a rainbow in it at the same time, that's a bullshit picture. It's completely fabricated. It's not real.
I have a quick question.
Yeah.
I've never seen a rainbow with the violet colors on top.
That was going to be the next thing I was going to talk about. And you're right. If you look at the rainbow, anytime you've ever seen a rainbow, red is on top. Right? Red is on top and purple is on the bottom. But I just drew this picture that definitely makes it seem like purple should be on top and red should be on the bottom, right? And trust me, the geometry does suggest that this is how it worked out. It's not just I botched it. Okay, because here's why we actually see red on top, even though red is the one that gets split onto the bottom. Okay, so here is this water droplet that does that. And then there are all kinds of other water droplets, right? So we got all kinds of rain stuff going on. And each one of these has the same sort of thing happen. All right, now imagine that your eye is right here. From this top water droplet, you're not going to see the purple line. The purple ray is going to cruise over your head. So does the blue, so does the green, so does the orange. But the red one, maybe I'll move it up just a little bit, but the red one's going to hit your eye. We'll just say that it hits your eye. Okay, so that means this water droplet is going to look red to you. All right, well, come down to say this water droplet, and we have the same thing happen. And so we get our purple ray, our red ray, and everything in between. This one, the purple is going to hit you. So this one's going to look purple. All right, well, what's this one going to look like? Well, it's going to be one of the ones in between. Because if the red does this and the purple does this, you're going to get something in between. Let's just call it green. And so that one's going to look green. All right, well, there's going to be one up here that looks orange and yellow and blue and so on and so forth. And so that's why when you actually see a rainbow, it's the red on top. Because that one up there, its red ray hits your eye, and all the other rays are going over your eye. You're not actually seeing it. And then as you move down, you start catching the rays that look orangish, and then the yellows and the greens and the blues and the so on down. So I'm glad you actually noticed that, Bradley, because a lot of times people are not aware of what they see, or they don't remember what they see. But yeah, rainbows are always red on top. Well, that's if there's one rainbow. You ever seen a double rainbow? That's a real question. I don't know. Has anybody ever seen a double rainbow?
I don't think so. For me, anyway.
Yeah. Okay, so from videos, oh yeah, and the rainbow guy, the guy who's down in like Yosemite or something. Like, oh my God. It's the rainbow. Okay, so you can actually get a double rainbow. I have seen a double rainbow. It does happen. If you look closely enough at next time, like a storm that comes through on a summer afternoon, look for it, and you often will see it. You get double rainbows when it's very, very bright. You've got a lot of light. And the reason that you'll get a double rainbow, remember when I was drawing this and I talked about all the other ones that were kind of bouncing around and all that? As we kind of followed it, there was another one that ended up coming out down here. I don't know if you remember that. Like there was the reflection up there and then there. I think technically it comes out over there. But there's going to be another one that comes out here. And it's going to do exactly the same thing. It's going to split again. But because of the reflections, it gets inverted. And so it comes out with red on top and purple on the bottom, which means when you see those, same deal, it's going to get flipped over, but it's also going to be much fainter. because every time there was one of those reflections, some of the light passed through the water droplet and so made it dimmer. So if you see a second one, the colors will be reversed and it will be much dimmer. I guess technically it would also be possible to see a third rainbow, but I don't know that anyone's ever recorded a third rainbow because I believe that the light is so dim by that point that you won't actually see it. All right, so this is what's going on with rainbows. I have now totally destroyed the magic of rainbows. Or we've explained it at least, which is kind of cool. So is there not a treasure at the end? Well, here's the problem. You'll never get to the end of the rainbow. I mean, and that's maybe the beauty of that myth, legend, whatever. Because the rainbow moves with you. If you start walking towards this, where the rainbow was, like, let's just say we're looking at this column of water that produced the rainbow. As you start walking towards it, the angles get all wrong and you don't see that rainbow anymore. So you'll never actually get to the rainbow because of the geometry. And in fact, as you move forward, you start seeing a rainbow that's coming from water droplets that are now behind the step. So another fun one, next time you see a rainbow, start driving towards it and notice that the rainbow always stays the same relative to you. You never get closer to it. You never get further from it. It's always just at the same place. So is there a treasure at the end of it? I don't know. I'll never make it there. But here's another fun one, and I like to think about this. So is a rainbow actually a thing? Is there such a thing as a rainbow? Is it an object? Let's think about that for a second.
I think it might be considered more of an optical illusion than an object.
Mm-hmm.
You know,
that's definitely my argument. This is one that it's funny. It's one of the things that recurs in conversations with my wife. I don't know if you guys have these things with people you've known a long time, where just like the same things come up all the time. For some reason, we always talk about rainbows, and she hates my interpretation of rainbows because I'm convinced no, a rainbow is not real. It doesn't exist. There's no such thing as a rainbow. What you're seeing are water droplets. You're just seeing water droplets that are colored, but they're only colored because of your position relative to them, right? Like I'll see this as a purple water droplet, but you might not because you're not at the same location, right? In fact, you might even see it as red if you're lower down on the ground or whatever, right? So I agree with you, Bradley, that I would say that rainbows are really, they're just optical illusions. They're our brain interpreting these things as having color, even though they don't really have color. So it's weird. It's totally weird, this idea of the rainbow. But you can also see why they were magical. And they were magical to lots of cultures, right? It wasn't just the Celtic, leprechaun kind of deal. All kinds of cultures, like the Greeks, is it the goddess? I think it was a goddess. I don't remember the gender on this one. There was a god or goddess of rainbows named Iris. That's why, like, the colored part of your eye is called the iris. And Iris was the messenger god. So they saw the rainbow as kind of like a portal for messages. It's the gods sending messages to each other. right? Or you go to Norse mythology, and it's the rainbow bridge, right? It's the bridge between worlds, and so all kinds of cultures had magical stuff to it. So does it need to be water? All right. So could there be a rainbow on Mars? So first of all, no, it does not just need to be water. It can be snow. You can actually get, we don't call them rainbows. I guess technically they'd be called snowbows. But you can get kind of the same thing happening. And you also get this effect around the moon sometimes. Have you ever seen, it's called a halo around the moon? It kind of looks like a rainbow around the moon.
When there's like thin clouds.
Yeah, and what it is, it's going through the ice crystals. And that one, it's not retroreflection. That one's just dispersion as it's going through ice. I mean, that's this. Imagine that the light that's bouncing off the moon is coming out, goes through ice crystals, and you kind of have to invert this or rotate it a bit for it to be correct orientation. But we would be down here looking up at the moon, and so you'd see those colors. So it happens through ice. So could you see a rainbow on Mars? Well, you wouldn't see a rainbow, quote unquote rainbow, because rainbows technically are because of the water in the atmosphere, the water droplets. I honestly don't know enough about the like reflective properties of gases, like carbon dioxide and stuff that primarily makes up the atmosphere of Mars. So I'm going to guess not. Because I think gas molecules, because of the fact that they are so active and can move around, they don't really allow for the same kind of reflection as as you see with like ice crystals and water water droplets, because of their structure. So I don't know the answer, Victor, but I would say I would guess no. I would guess that there aren't going to be rainbows on Mars. So
What about heat waves? I know there's not really color to them, but you can see like the colors in the background. Do you know how that might work?
oh, I definitely know how that might work. So you're talking about the like if you look over hot pavement.
Yeah, like you're driving down 395 and it's midsummer.
Yeah, or like above a hood of a car that's running, and it
Yeah,
kind of looks like
exactly.
everything's all wavy and
Hmm.
wonky, right? Okay, yeah, no, I definitely know why that happens. I wonder if you guys can figure it out.
Well, I'm thinking at that moment, like off in the distance, like I said, it's usually hot out. So I'm assuming that the gas molecules in the atmosphere that are present right there are moving more rapidly than they would be right in front of you. And that might cause a little bit distortion of the visible light.
Yeah, I mean, that's exactly what it is. It changes the density, right? Like when you heat up, you guys remember in thermodynamics, right? That when you add heat energy, it does things like it excites the molecules and all that. And so these gas molecules are more excited. They start moving around more. It gets less dense. And let's think about how density of the atmosphere might affect light. What might be the effect on light of lowering the density of the atmosphere?
The velocity,
All right, what do you think it's going to do to the velocity?
it's going to slow it down if there's a higher density and increase it if there's a lower density.
Yeah, right? Because we already know that in a vacuum, if there's zero density, that's fastest. right? And so the more dense the air is, the slower the light's going to go. All right, so now think about what's going on. We've got varying density light or air, which means we're going to have varying speeds for the light, which means we have varying n values. So what happens if you have a different n value?
It's different velocity.
Okay, so we've got the different velocity, but let's think about that in terms of what we've just been talking about. What happens if you change your n?
The angle of reflection or refraction changes.
Okay, so you're going to change the angle of refraction. So think about that. Let's say we're looking at a tree in the far distance, right? And when it's really hot out, it looks like that tree is, waving or, whatever. It's doing weird things. Okay, so we see that tree because the light rays that are bouncing off that tree are coming to our eye. They're passing through the atmosphere. So they're going to bend a certain direction. But if all of our air is exactly the same density, or close enough, all the n values are the same, it's all bending exactly the same way. So every piece of that tree bends exactly the same way, and it still looks like it's a tree. Nice and rigid tree. But if along the way it's meeting areas of variable density, they're going to start bending in weird directions. So now you put that together. Well, this part of the tree, let's say it bent this much. Another part of the tree bends this much. To our eye, it's going to look like the tree is bent. Okay, so it's going to cause that distortion. But then if you really think about it, what you see on those hot days is not just that it bends, but it's like even like moving, right? Like it's wavy. In fact, I think that's the word I used to describe when I was confirming what you were talking about. So why is it wavy then? Well, think about those different density air pockets. They're moving relative to each other. Again, remember thermodynamics, right? Actually, that's not even thermodynamics, it's buoyancy from first quarter. So all of a sudden now, if we've got less dense, it's going to rise. The greater densities are going to drop. So that little pocket that's making it bend this way is moving. And so it's going to look like different parts of that tree are moving, which gives us that wavy appearance. So there you go. I mean, this is really cool. Now, with just, think about it. We haven't talked about a lot of stuff yet in this class. We've talked about the speed of light. We've talked about reflections and refractions and dispersion. And dispersion is really just refraction anyway. But with just that little bit, we can start explaining all kinds of optical illusions. So, but yeah, so yeah, I guess long story short, yeah, I know exactly why you see what you see when it's hot out. But now you do too. And you can see exactly where it comes from and how it, like, it's not anything new. And in fact, it's putting together like 3 or 4 different physical concepts. This is why I love physics, honestly, because you can describe the stuff that you see out in the world, and you can, and it comes from often multiple features, multiple ideas that you can kind of integrate together. But awesome question. I like that one. All right, well, now we got rainbows. Yay. But yeah, there you go. All right, so other questions about this? Kind of making sense, I hope. Obviously, it's tough for me to know where you guys are when I don't have you here with me. But, hopefully we're all kind of on board. All right. So let's talk about another kind of property or another effect that we see that is worth talking about. And that's polarization. So another question for you guys. Do any of you guys have polarized sunglasses?
Yeah, I do.
Yeah, you got it. I know that mine are, right? Ralph, you got them too. What's the point of polarized lenses? Like, why do we buy polarized sunglasses?
It helps with the sun, like so it doesn't hurt your eyes.
Okay, so yeah, sunglasses just in general we use that to help protect our eyes. But the polarized are even kind of better. And so Victor said they block some type of light. They do. They actually do help block light. And specifically, one of the reasons people get polarized lenses is to help eliminate glare from reflections. Like people that tend to like polarized lenses are like people that are fishermen. If you go fishing, polarized sunglasses will help you be able to look into the water instead of seeing the stuff that's reflecting off the surface of it. A lot of skiers, snowboarders out, especially winter outdoorsy folks, like them for the same reason. Because the light that bounces off of the snow and the ice, gets blocked by polarized lenses. All right, so polarization, really what it is it's about orientation of the electromagnetic waves of light. So you guys remember that electromagnetic waves have two parts. That wasn't a question. That's what you remember. I know you do, right? There's an electric field and there's a magnetic field, hence electromagnetic wave. Do you remember how they're oriented relative to each other? And that one is a question. All right, yeah, so they're perpendicular. Thanks, Victor. So if you were to look at an electromagnetic wave, there's a electric wave or electric field. So we'll call that guy, this is the E, let's say. And then there's going to be a magnetic field, but that magnetic field would be in the plane that's coming in and out of the board, right? So that wave would be doing this. So I don't know exactly how to draw that, but we'll. That's the B. And again, that's coming in and out of the board. All right, so there's an orientation to these waves because of the fact that the fields are this way. So here's what we're going to do. We're going to think about it as how is the electric field oriented? Because if we've got that orientation, we know exactly what the magnetic field orientation is. We could do it the other way, but I'm just going to go with, let's say we know the electric field orientation. All right, so if we've got a ray, so here's a ray, okay, the wave is propagating in this direction. And so let's say that I'll just draw a little arrow here like this. So that's our little electromagnetic, or that's our electric field portion of this. So the magnetic one would be coming in and out of the board. Right? So maybe this ray is oriented in this direction. Now, it doesn't have to be oriented up and down, right? It could be oriented in any old kind of direction, but it's always going to be perpendicular to the ray. because the waves are always perpendicular to the wave. Okay, now regular old light, like light that's coming from the sun, is not polarized. You turn on your light bulb, like an incandescent bulb, kind of a standard old school bulb, not like an LED or something like that. That's not going to have any specific orientation. All the waves that are coming out, some of them are going to be oriented up and down, some of them are going to be oriented left and right, and every other kind of combination that's possible. All right, well, polarization is making it so that all of these waves are oriented exactly the same way, so that they're all coming out with the same kind of orientation. All right, so this happens in lots of different ways. All right, so let's talk about how we can get polarization. Polarized light. Okay, so one, I'm just gonna make a list and we'll talk about all of these. One is reflection. Reflection will cause polarized light. It also can happen from scattering. It can also occur using filters. It can happen with crystals, just naturally in crystals. Yeah, and I'm gonna, under crystals, we'll talk about another man-made thing that does them, right? But there are a few others, but these are the big things that cause polarization. So let me just start with the whole idea of like filters and how we can do this. So this would be like how your sunglasses, your polarized sunglasses work. So if we've got some sort of a man-made filter, that's a sunglass lens, all right? These are designed in such a way that there are molecules that are all in order, all with the same orientation. All right, so this is going to be a molecule chain, right? It's a chain of some kind of molecule. I don't know what it is. I'm not a materials guy, but we're going to have all kinds of these all strung together that are all in exactly the same orientation. Okay, so I'm getting bored of filling that in, but it's like this all the way. All right, now imagine that you've got a wave coming in, a light wave coming in. It carries energy with it, right? And these molecules are designed such that when a wave comes in, let's say that's in exactly the same orientation with it. So this is the electric field, and it comes in this direction, right? So it's coming in like that. It's going to absorb the energy from that electric field. In essence, it's taking the energy of that wave. It's absorbing that wave of light. If something were coming in, say, perpendicularly, it's just going to kind of glide right past them. Because its orientation is it's going, say, up and down, and it hits this molecule, it just sort of slides right by it. Right? As opposed to if it were going up and down and it runs into this thing, it just like slams into it. If you had a wave that's coming at an offset orientation, so something like that, part of its energy is going to be absorbed and part of it's going to be allowed to pass through. The component that's parallel or in line with these molecules is going to get absorbed, and the part that's orthogonal to it going to pass right through. So something like this is going to lose some of its energy, but the part that remains is going to be oriented up and down. So by passing it through this filter, everything that comes out is all oriented exactly the same way. In my picture, they would all be oriented up and down. but obviously if we turn this a little bit, we get oriented anyway. But the result is it's all one orientation. Okay. So that's how you can do it using filters, and that's how polarized sunglasses are formed. You also have polarized lenses for like cameras. A lot of cameras have them. In fact, the person who invented this, have you ever heard of a Polaroid camera? Well, Polaroid, polarized, is because whatever company that was, I don't think it was Kodak, but whoever came up with that idea was actually looking at it for photography. Okay, so this is a man-made way of doing it by creating filters. Now we have some of these in the lab, and you guys should definitely ask Kathy to take them outside and kind of look at polarization through these lenses, because you can see all the effects, all these other effects that I'm going to talk about when you do that. Anyway, all right, so you can man-make it, but there are a lot of natural ways that they happen as well. So let's kind of talk about those. So reflection, this is probably the one where we see it the most, and the reason why polarized lenses really exist. Think about a surface here, like let's say this is a water surface. And we're going to have light that's coming down. It's going to reflect. And there's also going to be some of it that passes through. All right, now it turns out that as these rays, as they're coming in, depending upon what their angle is, depending on the angle that they come in against this surface, they're going to reflect and get polarized. And the orientation of the electric field is always going to be parallel to this surface. It's going to be more polarized the closer and closer this angle right here gets to being a right angle. If this is a right angle, this is total polarization. It's maximum polarization if that's a right angle. Now, if you think about that angle, it's actually formed, if we think about what we've talked about so far, we say that this is theta 1. This is also theta 1. This guy's theta 2. So this is going to be a right angle when theta 1 plus theta 2 is 90 degrees. So if that's perfectly, if those two actually add up to 90 degrees, you're going to get total polarization. There's a name for this. This is called Brewster's law, named after the scientist who came up with it and saw it. I think realized this experimentally and then started running the numbers and realized that, yeah, it's always at a right angle. But Brewster's law comes from this. So think about it. The angle that's going to create total polarization, it's going to depend on what the materials are. Because the materials are going to affect the relationship between theta 1 and theta 2. Right? I mean, we already saw that with Snell's law. It'll write n1 sine theta 1 plus or equals n2 sine theta 2. So if you actually do the numbers on it, run a derivation of this with Brewster's law, it turns out that that angle, this angle, to get maximum, this is called Brewster's angle. Right? So the one that actually creates maximum polarization, and so we'll call that theta sub b. It turns out that you can calculate that you get that the tangent of it is actually a ratio of the two n values. So the tangent is equal to n2 over n1. I'm not going to bother you with the derivation. It's some trig. I mean, I love the derivation of it, but I'm not going to torture you with it. All right. Well, anyway, so the point here is that when you get reflections, you're going to get polarized light. All right. Now, if you slap on some polarized sunglasses, if their orientation, if we build it such that that orientation is perpendicular to the orientation of the reflected rays, it's going to absorb most of that light, which means it's going to eliminate that reflection. All right, so this is why people that go fishing like it, people that are skiers like it. It helps with driving because you get the light that's reflecting off of the roadway. Same thing. This is going to help cancel it down. Now, even if those rays aren't coming in at exactly Brewster's angle, there's always some polarization with the reflection. And so polarized lenses are going to help with it regardless, but there are going to be certain times where it like really cancels it out. If we were on campus, and this is something I think Kathy probably does too. I like going right outside the chem lab, and look at the windows either to Kathy and Sean's office or to the D108, the room where we usually have physics class. And if you stand there, you'll definitely see reflection. You'll see the trees that are further over that are reflecting off of that glass. You hold up a polarized lens, and if you turn it just the right way, that image of the reflection disappears. Completely disappears. If you rotate it again so that now it's not perpendicular, the reflection comes back. So it's pretty wild. I definitely suggest you guys pester her a little bit and say, hey, can we go? Bruce was saying something about looking at reflections and polarization. She'll probably know what that means. And you can also see that if you change the angle, you change what angle you're coming in at, you'll see the change in the effect, that there is an angle that's better than others. So you can even actually find Brewster's angle by moving yourself around until you get to a point where the reflection is completely gone. Anyway, so it happens with reflection. It also happens with scattering. So think about the light that's coming down from the sun, comes into the atmosphere, starts hitting all the molecules that are in the air. The molecules are going to absorb some of the light, some of the energy. And it turns out that it does kind of the same thing as with the reflection, that certain angles cause more polarization from just the light scattering off of them. So if you have polarized lenses and you go and you look up at the sky and you rotate the lenses, you'll see that there are times where it gets lighter or darker. When it gets darker, you're actually canceling out more of that scattered light that's polarized. So that's another fun one too. When you're outside looking at the reflections on the window, take a moment and hold it up to the sky and rotate it. And you'll see that it gets darker or lighter. You don't even need those. If you've got polarized sunglasses, you can go outside and do the same thing. And in fact, that's how you can tell if your lenses actually are polarized. If you've ever wondered, you're like, man, are these things actually, do I have polarized sunglasses? Take your sunglasses, go outside, look up at the sky, and just tilt your head back and forth. See if there's any kind of change in brightness. If there is, they're polarized lenses. If they're not. Okay, another place that you'll see this naturally is with certain crystals that will cause your rays to split into two. They're called birefringent or birefractive. So there are certain molecules and certain structures in crystals that will cause a light ray that comes in to refract in two different ways. So you actually get two different paths. And again, it's totally just due to the crystalline structure. But what's really kind of wild is that those two rays have different polarization. So the light that's coming out of them, if you have a polarized lens, can actually cancel out one of them, but not the other. So that will happen with certain crystals. You also see this with a lot of monitors, specifically the LCD monitors. If you've got one, the LCD, right, the liquid crystal display. Those crystals are such that the light that comes out of them is also polarized. So if you have polarized lenses, you can rotate a little bit and it will make the image disappear. I'm trying to remember, I think it might have been maybe my first smartphone was such that its polarization was in line, or it was perpendicular to my sunglasses. So if I ever took out my phone to look at it and I had my sunglasses on, it was a dark screen. But if I just tilted my head a little bit, then I could read it and I could see it. So whoever designed that phone, and I don't remember who it was forever ago, but whoever designed that phone did a really shitty job, because all polarized sunglasses are always oriented the same way. And yeah, that phone was such that I couldn't actually read the screen. So good job, guys. But have you seen those privacy screens that people put on their monitors? You know, the ones I'm talking about, that like you slap it on the monitor, and if you're right in front of it, you can still see everything on the screen. But if someone's looking at an angle, they can't. Give me a thumbs up if you know what I'm talking about.
Yeah.
Yeah. Like you'll see those, go to student services, you know, sometimes like signing up for classes or whatever, they've got them on, right? You can see them. Well, those are polarized because they're doing exactly the same thing. They're oriented such that when you're looking straight on, your angle, it's not a reflected angle, but it's the same kind of idea, but your angle is such that there is no polarization. But as you move to the side, your angle changes, and the next thing you know, it gets polarized and you can't see it. So polarization is a thing that's really useful, actually, and a lot of things are designed with it, but it's just another quirky thing that can happen with them. All right, you know what we're gonna do? Let's take a break. I've been talking here for a while, so I'm gonna pause the recording and just take a real quick break. I need to get some water and stuff. And then when we come back, we'll start talking about reflections and what we see in mirrors. And we'll start doing what we call geometric optics, which is looking at images. Where image is going to be, what are we going to see when we look at things in mirrors and lenses and all that. All right, so let me go ahead and pause, and then we'll come back in a little bit. All right, so let's, now that we started seeing how light works and all that, let's start looking at images, the images that are going to be formed due to these things, due to reflection and due to refraction and all that. So we're going to start though with mirrors, because mirrors are probably a little bit easier than lenses in terms of how they behave and what they do. So we're just going to start there. All right, we're going to start images formed by mirrors. Now, the most important thing to remember when we're doing any of this stuff, when we're trying to think about what we're going to see, we have to remember that our brain is always going to interpret that the thing that we see is at the end of the ray that's coming to our eye, right? So like, for example, I look at the whiteboard, I see this eraser here, and my brain tells me there's an eraser here because the light that bounces off of it comes to my eye, and my brain backtracks. It follows that ray back and goes, oh, yep, that's where this is. So this is a real object right here, and it's not that my brain is being fooled or anything. No, that's exactly where it is. The reason I'm bringing this up is that when we start looking at images formed specifically from mirrors, our brain's going to lie to us. Our brain is going to think that these objects, these things, are somewhere that they're not, because it's just going to backtrack those rays, see where it is. Now, let's start with an easy mirror. Let's just think about a nice, straight, planar mirror, right? Like the one that's in your bathroom. So think about this. When you're in the bathroom, you're brushing your teeth in the morning, you see your evil twin, right? You got an evil twin. Where is that evil twin?
In my head.
Okay, so in your head. Where's your evil twin appear to be?
Like in the mirror.
Yeah, it definitely looks like your twin is in the mirror, that it's on the other side of the mirror, staring back at you, making the same face you're making at it, right? But it appears to your brain that your evil twin is behind the mirror. All right. Why? Why is that what we're seeing? Well, let's just do a little bit of geometry and see what happens when we've got a flat mirror. So here's what we're going to do. Here's a mirror. And we're going to put an object somewhere in front of the mirror. So here is my object. Now, I am going to pretty much always use arrows as my objects, because the arrows are going to have orientation. So we'll be able to kind of see what happens if they get inverted and stuff like that. So they've got orientation, and they're really easy to draw, right? Just a line. So I'm going to use arrows. You'll see different things in different texts and all that, but I'm just going to use them. All right, now here's what we're going to do. We are going to think about light rays that are coming out of this object, and we're going to follow them. We're going to see where they go. We're going to see how they reflect. We're going to follow those rays. And we're going to do pretty much what I'm going to do is I'm going to do rays from the top and rays from the bottom. So we'll follow where the bottom goes, where the bottom rays go. We'll follow where the top rays go. And then we'll just figure that our object is still going to be between those 2 points. All right. So let's start with the tip of the arrow. There are going to be light rays coming out in all different directions. Like if this is our arrow, let's just say it's the eraser here. There are light rays that are bouncing off of the top, going in all kinds of different directions. And we know that there are light rays going off in all different directions because people can see this all over, right? Like if you guys were all in the room with me, you could go to different places in the room and you would still see the top of this whiteboard marker or eraser, right? So that means that there are rays that are going all different directions. Okay, so I'm going to pick a couple of them. I'm going to start with a ray that, let's just say, goes straight to the mirror. When it reflects off the mirror, which direction is it going to go? If that ray comes in perpendicular, which direction is it going to go?
Wouldn't it be perpendicular as well?
Yeah, it's going to come right back out because the angle, right now, what's the angle according to Snell's law? What angle does this one have?
90. Or would it be 0?
It's 0. Remember, it's always angles is from the perpendicular. So this has an angle of 0. So sine of 0 is 0, which means when we do the inverse sine, we're going to do inverse sine of 0, which is 0. So it's just going to bounce right back. Oh, I went Snell's law. We didn't even have refraction. It would still have 0 if it's Snell's law, but it's just going to come right back up. Okay, so this one's just going to continue and then come straight out. All right, so whatever that ray is, it's going to hit the mirror and then come straight back up. All right, so let's do another ray. And let's do it so that it's not going in perpendicularly. So we'll send another one out, say, this direction. All right, now, what that one's going to do, if we think about our perpendicular right here, it's going to reflect at the same angle. So it's going to do something like that. All right, so there are 2 rays. We could do bunches of them, but 2 is going to be sufficient for us to know what our brain interprets. All right, so far so good. A couple of easy, just a little draw some arrows and see what happens. Now, here's what I want to do. I want to backtrack these rays. I want to think about what my eye and my brain is going to interpret. So if I'm standing over here, right? So we're over on this side, right? Staring into the mirror. Our brain is going to think that the image is somewhere along this ray, but backwards, right? So I'm going to just draw this back here. Because there's a ray that's coming straight out of the mirror, I'm going to think that the image is somewhere along that line. Well, same thing with this ray. My brain's going to think it's somewhere on this ray, so I'm going to backtrack it. So my brain is going to think that the top of this arrow is on both of these backtracked lines. Well, that's going to be where these come together. So I'm just going to put a pink dot there. That's where my brain thinks the top of this is. It thinks it's behind the mirror. Just like you see your evil twin behind the mirror. Now, the same thing holds for the bottom. If I did the same thing, let's do a couple of rays for the bottom here. I'm not going to do any that are perpendicular because those are boring. So let's say we come in down here. It's going to reflect off like this. Maybe here's another one. Let's send this one up a little bit. Okay, so then it's going to reflect off like so. But we can do the same thing and backtrack both of those. So if I backtrack this ray, and I backtrack this ray, probably a little bit better. My brain is going to think that the bottom of the arrow is where those rays come together, which is right here. So there's my bottom, there's my top. And so there's the image. So in the language that we're going to use, this guy is an object. What the brain is going to interpret as the location of the image, this is going to be its image. So if you think about in the morning when you're brushing your teeth, you are the object. Your evil twin, that's the image of you. Okay, so those are the words that we're going to use here. There's the object and the image. All right, so the question is, where is this thing? Well, we already know that it's behind the mirror. But if you do just some like really easy geometry, like really simple geometry, thinking about the angles and whatnot, right? So think about this angle right here. That's the same as this angle, which is the same as this angle from reflection, which is the same as that angle, right? So those angles are the same, which means that these two sides are the same because it's an isosceles triangle. We also know these two angles are the same because they're right angles. So we have angle, angle, side congruence, which means those two triangles are congruent, which means these distances are the same. So in a flat mirror, the image of every object is exactly the same distance behind the mirrored surface as the object is in front of the mirrored surface. And I know you're all going, well, yeah, duh. We've seen that. Yeah, but it's nice to know that at least the laws of physics say that it must be that way, and so we can describe it. I mean, that's another fun thing. Have you ever like, I mean, you might have, but next time you're in front of the mirror, take your finger and do the ET moment with your evil twin. Right? Get your fingers together. And you'll notice that your fingers actually never touch. Check it out. You'll see that you actually never get your fingers together. There's always a gap. And next time we'll talk about why that is. See if we can figure it out. All right, well, anyway, so we got our object, we got our image, and we see that these distances are the same. Now, the way that we're going to specify these distances and all that, I'm going to do my best to stick with the book. I'm going to try to stick with the book notation, which is slightly different than the notation I learned. So if I start throwing in like P's and Q's and you're like, what the hell is that? Remind me. Oh, yeah. Okay, so DO, this is going to be the distance from the object to the mirror. So in the picture that we have going on here, this is DO. That's the distance from the object to the mirror. For the image, that's going to be DI. So this is going to be the distance from the image to the mirror. So again, in our picture, that's DI. So like I said, I learned it with P's and Q's. P is your distance to the object, Q is your distance to the image. So if, just because no, not if, when that happens, when I start going, oh, so 1 over P plus 1 over Q, stop me, and I'll stick with the book. All right. So anyway, I will do my best to stay with book notation. All right. So with flat mirrors, we see that DO equals DI. They are actually equal to each other. But that's not going to be the case once we get curved mirrors. Okay. So let's start talking about those. Oh, one more thing. In terms of these distances, we do have sign conventions, positive and negative for the two sides of the mirror, because it's going to turn out sometimes our images are on the same side of the mirror as our object, and things like that, like weird things can happen. And so when we have things behind the mirror, those are negatives. So what we actually have here, if we're talking about a flat mirror, is that DO is equal to the negative of DI, because the image is behind the mirror, so DI would be a negative number. So we have to change the sign to make it positive for the DO. Okay, so that's the convention with mirrors. Things that are going on in front of the mirror are positive. Things that are going on behind the mirror are negative. And then one other thing I want to mention before we get to the curved is the difference between real and virtual. All right. In this case, this image is what we call a virtual image. Because it doesn't actually exist, right? There's no evil twin of you behind the mirror. The way that we know whether it's real or virtual is, do the light rays actually pass through that object? So if you think about this image, we never had any of the actual light rays hit it. The actual rays were the blue and the green things that I had here. We backtracked them to find our image, and that's why it's virtual. Okay, so again, real, this is going to mean that the light rays pass through it or touch it, and virtual is going to mean that they don't. So in this situation, our object was real because the light rays were coming from the object, but the image was virtual. And we are going to see real images sometimes. A real image is one that you could actually like project onto a screen. So we'll get real images, we'll get virtual images. Objects are usually real, but we'll also get virtual objects sometimes.
Is a virtual object a shadow?
A virtual object would not be a shadow, but it would be like, let's say we had a combination of mirrors. Let's say there was like a second mirror here on this side. The image of us is going to be an object for the second mirror. Right? You kind of see what I'm saying there? And so this object for the second mirror is actually virtual because the light rays aren't going through it. So that's what usually leads to virtual objects, is there's something else that's creating that object through lenses and mirrors. So
Okay.
I know it feels weird because it's like, well, no, like this is a real thing. I can hold it in my hand. I put it in front of the mirror. It's real. But sometimes images become objects, and yeah. All right. So we cool with the flat mirror. Pretty obvious, right? What's going on? But it's always the same distance away, but behind the mirror, because it's going to be virtual. Okay, so let's curve these mirrors. Let's make it so that they're actually spherical. All right, so we're going to look at spherical mirrors instead of planar mirrors. And these are all over the place, by the way. You know your car mirror, the one that says objects are closer than they appear, and the one that's over on the passenger side.
Yeah.
That one actually has a curve to it. You'll see these sometimes actually on kind of blind corners. You'll see them up, like there's one in the college on the way down to the computer lab. I don't know if you've ever seen it up in the corner of the hallway there in the D wing. So you got those. You can think like a spoon. A spoon's got curve to it. So we're going to look at spherical mirrors. And we're going to go that they're actually circular. So that they've got a radius of curvature. Obviously, if we change the shape, we're going to get different things are going to happen in terms of reflection. But we're going to look just at spherical. Now, there are two ways we could have this mirrored surface. We could have it so that the mirrored part's on the curve that's bending out, or it can be on the part that's going in. And so we do have names for those. I'm sure you've heard concave and convex. We are going to do the same with spherical mirrors. Okay? So you can have concave and convex. And all this means is that the mirrored side is inside the curve if it's concave, and convex means that the mirrored side is outside. All right, so let's start with concave. Let's look at what happens when we've got a concave mirror. So a concave mirror would be, here's our mirror that's curved, and we're going to have our object somewhere out here. And we want to see what happens to its image. All right, so we're going to do the same thing. We're going to do the same thing that we did with the flat mirror, which is we're going to send out some rays. And we're going to see where do those rays go. And then backtrack if necessary to see where those pieces were. All right, now, before we do that though, I do want to mention that when you have a concave mirror, if the angles are small, good old small angle approximation, so if these rays are coming out at very small angle, a circular mirror will have a focal point. You remember focal points?
Yeah, with
Like,
ellipses.
with parabolas and ellipses and all that. Yeah, you have the foci. So basically what's going to happen here, if we've got a circular mirror, if you were to send in a whole bunch of parallel rays, because of the geometry of this, they're all going to bounce back, and they're all going to bounce back and pass through the same point. And so that point right there is called a focus. Okay, so it's a focus, or sometimes it's also called a focal point.
Now, are these rays reflecting or refracting at this point?
They are reflecting.
Okay. Just wanted to make sure.
Yep, this is a mirrored surface. So they're just going to hit and bounce right back.
The reason why I asked is it made me think of a telescope.
Okay, because when you have refraction and you have lenses, they also have focal points. And we will talk about that when we get to lenses. So refraction will lead to the same kind of thing, but for a different reason. Instead of then being reflected back to the same point, they're all going to get bent such that they all go to the same point. So I'm not surprised that it made you think about telescopes, because we also talk about focal lengths and all that with like telescopes and binoculars and even like eyeglasses, because that's how they're designed, to take light and focus them to a specific place. But yeah, this is all reflective. Right? Okay, so the question is, where is that focus? Well, it turns out, and you can do a little bit of geometry on this as well. I'm not going to bore you with it, but it's in the book. You can definitely look at it. But if we have small angles, right, and I keep saying that because I want to stress it. So for small angles, we have that the focal distance. If we say, call this distance from the mirror to the focal point, call that F. It turns out that that focal point is 1/2 the radius of the circle. All right, so there is a focal point, and we know where it is. All right, it's going to be 1/2 that radius. Now, why I bring that up is because some of the rays that we're going to use to figure out where our objects are going to be, or our image is going to be located, are going to make use of the focal point. Okay, so there are actually 4 rays that we can use when we've got a concave mirror that are going to be useful. They're going to be pretty easy to do. Okay, so let me show them to you. The first one, so let's start at the top of the arrow. The first one is going to be the one that, well, actually, let me do this. Let me mark on here where a center would be. So let's say that this is the center of the circle. So that would mean this is our radius. So our focal point would be halfway from that to the mirror. Okay, so let me go just mark it. All right, so here are the 4 rays we can use. The first one is going to be the ray that comes in nice and straight here, nice and parallel to the center of the mirror. Because what we know that's going to do is it's going to come and bounce through the focus. Okay, so that's one really good ray to use. A second good ray is the one that goes through the focus. Because the one that goes through the focus, when it reflects, it's going to come out parallel. So this is actually enough for us to see what happened. Because now look at what we know about the top of this. The top is going to appear as if it's coming off of this red ray. And it also appears that it's coming off of this teal ray. So it's going to have to come from where they are together, which is right here. So the pointy part of our arrow is actually going to show up down here. All right, so those are 2 really good rays that I use frequently. Another good ray, if this is our, let me draw that. Oh, axis here. So a third good ray is the one that goes to the mirror at that central point. Because this one, since this line is a radial line, it's perpendicular to the surface, which means the angle of reflection is going to be exactly the same as the angle that this just came in on. Right, so those two angles are identical. So there's a third really good ray. And notice, even with my suspect drawing, all three of those are coming in together at the same place. All right, so there's ray number 3 that you can use. And then ray number 4 is the ray that goes through the center. All right, so it just goes straight through the center down this direction. Now, I love this ray. I absolutely love this ray. Because think about it. It's on a radial line, which means it's coming in perpendicular to the surface, which means when it reflects, it comes right back at itself. This is very similar to the one when we had the flat mirror, and we just went straight in perpendicular. Okay, now, this is where we can see the issues with my drawing, and I probably didn't actually cut that exactly in half and everything, but all 4 of these rays, the teal, blue, red, and orange, should all come together at the same point. It's mostly there, right? But basically what we know, let's make it a big point, somewhere in there, right? That's where the pointy part of our arrow is located, at least in terms of the image. Okay, so then what about the bottom of the arrow? Well, you can do kind of the same thing, but what you're going to see is that the bottom of the arrow is still going to be on this central axis. So what we get for our image is this guy down here. Cluttered it way too much, so let's just do this. Forget about the orange one, since that's the only one that didn't really play well with the others. All right, so here was our object. And there's our image. So check out what happened with this one. This one got inverted. The image we're going to see is actually upside down from what it was before. It looks like it might be a little bit shorter. No, we'll figure out. There's an equation that allows us to determine magnification. But it's been inverted. All right, but is this image real or virtual?
It's real.
Yeah, this one's a real image because the rays are actually passing through that point. So for this setup, and I want to just stress that this is just this setup. It's not always with concave mirrors that you get it, but it's concave because of where the object is and all that. But this one, turns out that this image is real. Meaning you could actually project this onto a screen. Like if you were to put a little piece of paper here, you would actually be able to see the image of your object on that piece of paper. We also have these things in the lab. We have concave lenses that you can project onto a screen. And I'm sure Kathy will have you play around with those as well. All right, so these are the rays that you can use. Sometimes you're going to get real images. Sometimes you're going to have to backtrack and see that you get virtual images. It really just depends on how everything is oriented. Let me show you another one that would make it the same deal with concave lens that doesn't give you a real image. So let's try this. So here's a mirror. Here's our central line. Center line. I have no idea where the center of this is, so let's just wing it. Let's say that that's the center, which means half that distance is the focal length. So maybe that's right there. And let's move our object nice and close to the mirror, because this will also show you how we have to deal with ones that, like with the going through the focal length and stuff when we don't actually go through the focus. So let's say this is our object. So again, think about the 4 rays we can use. We've got the one that if it comes in parallel to the central line, is going to bounce back through the focus. Okay, so there's that one. We also have the one that if it went to the center line, it bounces back at the same angle. All right, but now the other 2, these are where we have to get a little creative. Because think about the one that went through the center. If I just take a ray that goes through the center, it's not going to actually reflect off the mirror, right? So what I have to do is I have to think about that radial line that's coming out from the center and continue in that direction, right? So here's that radial line. So it's going to come out in that direction. It then reflects and comes back through the center. The one that went through the focus, the red one, we have to do kind of the same thing. We have to project from the focus and have it run in that direction so that it then bounces out parallel. So you have to do something differently when your image is on the inside of the center or the focus, because you now aren't going to send a ray through those points, but you're going to take the ray as if it had gone through those points and continue on. All right, but now notice that these rays don't all come together at one spot. So what we would have to do is backtrack them. So the red one backtracks here. Let's see, the blue one backtracks like that, right? And then you can do similar things for the orange and the teal. Let's see how lucky I got here. I'm not feeling it, but let's see, this one backtracks. That's actually not too terrible. And then the orange one, it backtracks. Oh, that was actually better than the first one. So notice that those all come together right around here, which means that's where the top of this arrow is going to be. And so there's our image this time. So we started with an object here, and we ended up with an image on the other side of the mirror. So this time, our image is virtual. Because the light rays don't actually pass through it. They just appear to come from it. It's also on the other side of the mirror. So in terms of its distance, it's di. This di is going to be negative. This di is going to be positive. This one didn't get reflected. It's actually got the same orientation, but this one's bigger. It actually got magnified. So in terms of orientation, up or down, magnification, like getting bigger or smaller, staying the same, it really depends on everything. It depends on the curvature of the mirror. It depends on where is our object relative to everything. So there is a formula, but we'll get to that next time. I don't really want to derive it because we've only got a couple more minutes here. But we're going to pick up where we left off on Tuesday, where we come back to this and we actually build the equation. We look at what is the equation that relates these distances between the image and object distances. We're just going to need to use a little geometry to do it, but it's kind of nice. The end result is a really easy equation, and we'll also then create an equation for magnification so that we don't have to rely on our drawing ability, right? Like doing this, we're relying on our drawing skills. And if you're like me, that's questionable at best. So if we can have an equation where we just plug stuff in and say, okay, we've got a 10 centimeter tall object that's 8 centimeters in front of a mirror with radius of curvature 6, like if we've got all those numbers, we can just plug it in the form. All right, so that's what we're going to do next time. So just so you guys know, we're in chapter 2. We're a little bit ahead of schedule, and I figure we're going to try to stay ahead as long as we can, because eventually we'll fall behind. But we're in chapter 2. Chapter 2 is all this geometric stuff. So we're done with chapter 1. You should be able to go in and do the chapter 1 homeworks. So try those out. And on Tuesday, we can definitely talk about some, because I'm sure there will be questions. All right. But other than that, I'm going to wish you guys all a very happy weekend. And I will see you all on Tuesday. All right. So I'm going to go ahead and pause or stop our recording, and we'll call it